Hey, and welcome to the final week of Reproducible Research in R, course being taught at LSU to largely graduate students, but aimed at upper level undergraduate students and beginning grad students. So this is week 12. Last week was week 11. I mispronounced that in the last lecture. Sorry about that. And today we'll be sort of rounding out our exploration of R with a little bit about actually how to go about analyzing some of the sort of real data, but mainly on like principles of sort of modeling, starting with just linear models in a sense. We haven't even touched that. We've mainly been focused on data manipulation and tools for reproducible research. But so much of the research that you will do is focused on sort of the output of statistical models. I'll teach this from a very frequentist perspective. And so those interested in sort of Bayesian modeling, you'll have to look elsewhere. Richard McElrath has done an amazing job in his book, Statistical Rethinking, exploring Bayesian concepts. And then here at LSU, we have Brett Eldred, who teaches a course in quantitative ecology that deals with more Bayesian modeling, and even goes into a lot of like maximum likelihood estimation, things like that. We will not go into optimization here. Yeah, so very basic. I'm going to teach you sort of principles of modeling from a very sort of simplistic sense. And without further ado, I'm going to share my screen and then we can sort of go from there. And so I'll be teaching from gedit and the terminal, because last lecture our studio was just like not working. And I don't want to deal with that. And also we'll be creating a few plots that I just sort of want to immediately appear as a sort of separate like X11 window and not as the inline thing that our studio does. So sorry about that. Hopefully it's clearer. But yeah, and so the reading for this week is sort of an almost classic paper at this point. It's from 2001, but I think it's really cool to start to think about what the point of modeling is, what we want out of a model. And so Leo Breiman in 2001 said like there's two schools of this sort of statistical modeling, one of which aims to get at inference and the other aims to get at prediction. It's a little bit of a line in the sand in the sense that models aimed at prediction can also do a really good job at inference. I'll leave that up for sort of debate in the other lecture that I have with grad students, and also like sort of you on YouTube to sort of read the paper and take it as you will. The focus for most of the lecture will be on inference, but the end of the lecture will sort of shift and I'll talk more about prediction. Okay. So a lot of ecology, and I think science in general, draws this weird distinction between like modelers and more like boots on the ground, or muddy boots, quote unquote, ecologists or scientists. And it's been reinforced, I think, in a lot of negative ways from sort of classic scientists in the field. I think it's really counterproductive. And so to sort of define what we mean by modeling, it's actually fairly ambiguous and fairly simple, is that when you create a sort of model of something, either statistical, phenomenological, etc., you're basically just trying to describe a system of interest. As I define it here, either for the purposes of sort of inference or prediction. So we make a disease model trying to fit it to data to get parameter estimates, or we fit it to different populations to look at the effect of a response, or even like an ANOVA is a linear model looking at the comparing means of different groups, sort of treatment groups. So you expose one group to treatment A, one group to treatment B, and you want to see, is there an effect of this treatment on some outcome variable? So I will focus largely, if not entirely, on linear models here. And yeah, this is an ambiguous lecture, but I think it'll be hopefully fun and hopefully informative. Check out the lecture notes on GitHub, link to them in the description, hopefully. I think maybe the most telling sort of quote that is indicative of sort of this lecture is a sort of paraphrased quote from Alan Hastings, where he said, and it's in the lecture notes right here, when you create a model of a system, you have two things that you fundamentally, or that you don't understand. The system that you're trying to sort of predict or get at due to sort of error terms and other things, and the actual model itself. And so we build in a lot of like inherent assumptions when we model something. And that's something we need to be cognizant of as we move forward. And you'll see that in a couple of different examples when I sort of show you in a really simplistic sense in R. And so what is a model composed of is essentially some response variable that you're interested in. And so I go into this in the basic components of the model, where we have some response variable, typically set a y. Y is our response variable that we sort of want to predict, and the explanatory variables are those that do the predicting. We want to explain variance in our response or predict our response variable as a function of some set of explanatory variables. And so to do that, I'm going to open up R in the terminal. So we have our lecture notes on the left and R opened up on the right. And so I'm going to go through a simple example where I just generate this random variable from a uniform distribution bounded between 0 and 1 that I say is my y. And then I'm going to make a variable x that is a function of y, but just with the noise of another uniform distribution, another uniform random variable between 1 and 4. And so here the relationship between y and x is clear. And so we have this sort of simple polynomial relationship where y squared by this random noise term is our x. So x hypothetically should have, it doesn't hypothetically, it has a signal of y. And so we can model this using Lm, which is the sort of simple linear model structure in R. To look more at sort of the assumptions of Lm, we can use our manual function. So put the question mark, see Lm, and you can see it has a bunch of just sort of arguments that go in base. After this, I think we'll use GLM for the most part, which allows you to look at different sort of error families and things like that. And we'll get to that in a second. But here we assume that y and x are linearly related. And so we can create a model by using the formula interface in R, which is your y or your response, and then this tilde character. This enters sort of the formula interface in R by some variables x, or you can add to them, say x plus some other variable. We'll also go into interaction terms in a minute. But I wanted to keep it very simple to start off with. And we have this model of what y and x look like. And so we can quickly plot out what y and x will look like, which is this code here. So this will open a new, I'm going to move it up here to the top right. And so now we see our relationship between our response variable y and our predictor variable x. And there is a relationship. It's a very sort of clear relationship that we imposed on the data. And we can look at the model fit to these data using AB line. So AB line, you can handle a model object, and it will, at least in terms of LM or GLM, and it will plot the best fit line to those data given a single predictor variable. And so what this line is attempting to do which I didn't really sketch out, and you can see in other places. I'll highlight it with the cursor here, but essentially we're trying to just draw a line that minimizes the error between this predicted line and the actual data. And so this predicted line and actual data, these points are actual data made up, and the line. And so it's trying to minimize this distance, this vertical distance, just in y dimension, between each point and this line. It's an important concept to know. And it's important for a lot of reasons here demonstrated by the data that are just sort of clearly nonlinear. And so if the point is to just minimize this distance in between our data and our best fit model or our understanding, maybe it makes sense to make this line a little more bendy. If that makes sense, right? We don't strictly need this linear model if the point is just to minimize the distance between some line, squiggly, not squiggly, and the data itself. And so that's what I do down here. And here I'm just fitting a spline. And so I'm going to plot the data again, but now instead of that linear model that we made with all of its assumptions, I'm going to plot a smooth spline. So splines allow for curvature in the data. And you see it sort of captures this lower bound issue where when x is less than 0.2, it tends to sort of have this polynomial relationship that I imposed up here with this term, when I defined x, essentially. And that is like a better fit to the data, right? And so you see the differences, but you also see the red line tends to agree with the data a little more. And sort of why do we not want to do this? What's the problem with fitting a spline when it explains a lot of the data, but it limits the sort of inherent inference that's there? Especially, I think as Brian points out in that paper, what you can do in terms of prediction. And so predicting either beyond the bounds of the x variable that you've observed, which is here is bounded between 0 and 1, or even sometimes sort of within this range, but with new data. And so this fits, the spline sort of inherently fits a little bit to the noise in the data. And we get at that here by, I'll run through this top code. This just plots out what we had before. So these are the data that we're working with. This is the linear model as a black line. And now we think there is an inherent sort of polynomial structure. There's some curvature to the response between y and x that we put in there. And so if we incorporate this polynomial term here using the poly function in R and say we want a order 3 polynomial, which I'm highlighting there, we can fit this model sort of, so we have y as a function of some polynomial function of third order to x. And we can look at that, and it has 3 terms apart from the intercept. So it has an intercept, and then it has 3 different parameters which control the shape of it. We can plot that line, and that's what it looks like. And so the 3 polynomials basically give it 2 inflection points, one right about here and one right about here, where it attempts to find this curvature here in the data, and then also bends back here. And we can also look just really quick to explore. We can see just a second order polynomial, and we'll plot that in a different color, which I'm typing out as blue. And so let's quickly plot that out. Fairly similar, but here it only has a single inflection point, but it's still sort of sloping and capturing some of that variation down in this region. I'll undo that so that it matches lecture notes. But there's nothing inherently stopping us from fitting a higher order polynomial to the data. And so if the goal is just to explain variation in the data, why not have these 15 plus term models, this incredibly complex sort of polynomial, as sort of splines start to get in that territory, that sort of let the data inform the fit. And so we can plot out a 15th order polynomial, and here's what it's doing. It's trying to maximize the amount of variation that explains in the observed data, which appears to be a relatively good fit. However, this model itself, as stands, is really, really uninformative, right? So all of a sudden, look at the parameters that we have to estimate from the model. All of a sudden, we have an explosion of parameters we have to estimate. This model won't be transferable just like fundamentally to like any new data. And so it will likely do a really bad job at predicting. And it's really hard also to sort of gain inference from something so complex, especially given the data. And so one thing to always keep in the back of your mind when using sort of model selection criteria, so things like AIC, is that you're building the model given the data. If the data are flawed or have some inherent bias in them, you're fitting a model that incorporates that bias sort of implicitly. And so to acknowledge that is really, really important. And we'll go over sort of what that looks like in a simplistic sense in a bit with regards to sort of understanding Simpson's paradox or like what predictors to include in the model. But this right now is just a very, very simple model. I'm just trying to explain some variable y as a function of a single predictor variable x. But likely this sort of 15th order polynomial curve is probably pretty uninformative. But also that linear model fit to there is also like not that informative because this inherent sort of curvature in data. And we can look at that once we start breaking the assumptions of the linear model. So to break them, first we need to understand what the assumptions of the linear model are. And so the three sort of classic assumptions of a linear model, and it's true of generalized linear models as well, depending on sort of how you define the air family and the length function. But even then, some of them stay, are independence. And so when you sample a population or some variable, you're assuming that samples are not autocorrelated in space or in time. This is something that is broken in a lot of ecological systems due to what's called Toevler's law. So things that are nearby in geographic space tend to be more similar. So if you want to look at community composition or something, or population dynamics, you have to inherently account for the spatial correlation. The fact that nearby populations will inherently be more similar in their dynamics or their response to some predictor variable x, x1, x2, x3. The next is that they're identically distributed. And so samples must come from the same probability distribution. This gets at the sort of error distribution in a sense. And we actually won't dive too much into this assumption, I don't think, in this lecture. And then lastly, the linear model as it stands, the simple linear model assumes normality. It assumes that the samples and the error, they come from a normal distribution, a normal probability distribution, such that the errors of the y variable, the response variable, are normally distributed. But we can tweak that to handle that issue. And the tweak is to move away from linear model to a generalized linear model, which essentially exists as basically a linear model that just uses a link function to transform the response into something where it can then sort of fit in the standard sense. And so you're still trying to minimize the distance between the data and the actual sort of best fit line. But here, generalized linear models can be used for things that are just inherently nonlinear. And so this is actually a good example. The y variable that I chose and the x variable that I chose are inherently bounded between 0 and 1. I don't think that's actually true with the y variable, or sorry, with the x variable, but the y variable I drew from a uniform distribution, I set firm bounds on it. That goes against the normality assumption, in a sense, because the normal distribution is bounded between -infinity and infinity, and we have data that's bounded between 0 and 1. We're assuming the error is normally distributed. We're going to look at that assumption in a bit. But if you want to get sort of around that assumption, when you know your data are not, your response data are non-normal, let's say you're looking at survival data. And so survival data are inherently binomial, where it's did this organism survive? Yes or no? 0, 1. You can't fit a linear model with those data, but you can fit a generalized linear model using, I'll highlight it here, the logit link function. And so that essentially allows you to use the sort of structure and optimization of the linear model, but in application to different structures of data, i.e. those that only exist in between 0 and 1. And therefore the output and the sort of prediction will be bounded between, will bound the response between 0 and 1. So here I go over an example of logistic regression where we're assuming that the response variable y is binomial distributed according to some probability pi here, where that's the probability of success. And so in the survival sense, it's the probability that the organism survives. And so this is what we call, that some would call the random component. Meanwhile, the systematic component here are those explanatory variables, are x's here on the x-axis. And then the sort of traditional model framework of, and this looks better in the PDF compiled version, but basically it has some intercept where here, which is maybe right around 0.21, 0.22, and that's beta 0, beta sub 0. And then beta sub 1 is some slope coefficient, which relates the predictor variable in a linear fashion to the response variable y. But here, the y variable will be transformed according to the logit function to account for the fact that it is bounded between 0 and 1, and needs to be treated as such. And so here I go into what the logit link function actually looks like. Again, this is LaTeX code. It looks much better in the compiled PDF. You don't really need to know sort of what the logit function is. It's useful, but it's basically a transformation of the response data to make it more amenable to analysis in a sort of classic linear model framework. And so here we create, just to sort of show it off and show the model, we use new data, but still keep the old x just for fun. And so here we create y2, which we randomly pull 100 values from a binomial distribution with probability 0.5, which means that we flip a coin 100 times and assume it's a fair coin, meaning a probability of success, or 1, is 0.5, and a probability of failure is also 0.5. We can look what that looks like. It's a bunch of 0, 1 data. And then we can create a model object where we say, so we use GLM now, which is, we're still working entirely in base R, but we specify what error family it is. And so we say what family it is, and we say binomial. This is a binomial distributed response variable. And so now we can look at the summary. And so summary is really useful for exploring model output. And so I'll actually just type in M5. And so when you say just M5, it'll tell you a bunch of important information. It'll tell you the call that you made. It'll show you the coefficients printed to screen. And it'll show you information that's important in terms of the degrees of freedom that you have, the AIC, if you choose to sort of go down a model selection route instead of the other route. I don't want to say the other route, but if you choose to sort of compare models, right? If you had other predictors that you wanted to say, which is the best model given the data. Here, we're not doing that yet. However, summary gives you a little more information in terms of the significance of the predictor on the response variable. And so this is a statistical test telling you, is this slope, which I'm highlighting here on the lower right, of x different from 0? Does this variable have a linear effect on the on the response variable? And here it doesn't, and neither does the intercept, and that's because it's sort of random data, so we wouldn't really expect it to. But this is a sort of simple sense, and so we've already gone over, in a sense, how data structures can manipulate findings, right? And so there's other flexible. Not that GLM is inflexible. GLM is actually a fantastic resource and has a lot of built into it that it can do so much heavy lifting. I think I just want to introduce you to other forms of modeling that may be more useful in other situations. And so, yeah, hierarchical models. I'll talk about ridge regressions a little bit here. This is actually the only area I think I mentioned ridge regression. You may have heard of GAMs, or generalized additive models, which we won't go into here. It's more similar to sort of fitting that spline, where you smooth over the continuous X term as a way to sort of add it into a linear framework. Mixed effects models, which we also won't go into, but those are essentially a way to sort of parse out the effects of random effects to observe fixed effects. And so for many of us, we'll have multiple sort of plots within a single treatment, and you need to account for that variation. And so adding in a plot level random effect is important to understand the system itself. And then there's also like sort of flexible methods, like tree-based methods that allow variable interactions. And so instead of this single X, you have multiple variables, and let's say they interact in nonlinear ways. Tree-based methods tend to sort of outperform a lot of other approaches like linear models. Yeah, and so things like random forest, which I mentioned here, or gradient boosting machines, either in terms of XG boost or just like GBM. And those function in a way where they take a predictor, they take a response variable Y, and they try to break it down into a bunch of weak learning trees. And so maybe X1 explains some small proportion of variance, but X2 is like the next level down that explains some residual variance. You inherently sort of have an interaction between X1 and X2 that's accommodated for in tree-based methods, where it wouldn't be accommodated for when you consider it in a GLM framework, where your effects are assumed to be sort of not independent, but on the same level as the response variable. There are many way smarter people that are able to explain that a little bit better. Excuse me. And so at this point, sort of we've covered at least linear models and a bit of sort of the complexity of models versus their ability to not be overfit and actually be informative. And now we're going a little bit into, I call it feature creation, but it's not, I don't think I really go into feature creation here. So feature creation is the idea that maybe it's not temperature and precipitation that are important to population size, but it's the interaction between temperature and precipitation that is really important. And so we have to, maybe we can either incorporate that interaction directly into the model, or we can create a new feature meaning covariate, meaning one of our X's, that accommodates for that interaction. And so here I approach it in a simplistic way, where I create a y variable as I did before, but this is just going to be a new random draw from a uniform distribution bounded between 0 and 1. I create an x variable, an x1 variable that's inherently related to our y variable. And then I create an x2 variable, which is intrinsically linked to our x1 variable. And so here, like sort of getting away from the y variable, but both variables should be important. I mash that into a data frame. Here I have dat. I can look at the head of dat and see the covariates, where the first column is the response and the second and third columns are my two predictors. And I can look at what it means to have either additive effects or interactive effects. And so here we have Glm, the linear model call. We have y as a function of our x1 plus our x2. So I accidentally hit the wrong button and bounced around. But here we are. Okay, so we got that, we got that, we got that. And so now we can look at our additive effect model. And we can type that in, just typing in M6. We're gonna go into some of the logistical plots. There's a better, like the trace plots. It's not the trace plots, it's Bayesian. We're going to go into some plotting later about goodness of fit and ideas around that. That's not yet. And then we have our model that incorporates interaction terms. And so how they differ is up here we have coefficients that correspond to the independent effect of x1 and x2. And down here we have the effect of x1, the effect of x2, and then the effect of x1 given x2. We have the interaction term between them. None of these terms are the interaction term is likely to be not significant, just because the way we sort of structured the model. And so we can see a summary of M6, which is our additive model, and we see x1 is important, x2 is a little too far removed. And so x2 was that noise added on to x1 in an exponential fashion. And then we can look at our summary of M7 and see that it's slightly different. Oh man, oh, well, that's great. Okay. So we have x1 being significant. We actually have x2 being just barely, by frequency standards, significant by the arbitrary 0.05 threshold of alpha. And then we also have the interaction between x1 and x2 being significant. Which makes sense, given how we sort of structured the data. And so we took x1 to be a function of y with some noise, and then we took x2 to be a function of x1. So x2 is sort of inherently related to x1. And we can plot those out and sort of see that clear relationship between x2 and x1. So there should potentially be an interaction as long as it plays off of the relationship to the response y. And we can plot, I don't know what I plot out here. Oh, okay. So I plot out y as a function of x1 with colored by x2 to show a sort of clear relationship between x1 and x2, and also a sort of clear relationship between y and our response variables. So here the interaction term actually was pretty important in an inference in terms of the importance of x2, which is intrinsically related to x1 as we've defined it. I'm reading through the notes here. I give an example about beer, which I think I was grasping at sort of analogy straws at that point. And so here we're trying to predict the duration of time until a bottle of beer were to go bad. And we have predictor variables such as bottle opacity, and so how much light can get into the bottle, and then maybe dimensionality of the bottle, or even sort of something like temperature or the total amount of light. And so here, I think I chose opacity and dimensions as a way to actually measure the important aspect, which is how much light is getting into the bottle. So if you had a completely flat bottle that's really big, the surface area would be so great that bottle opacity probably wouldn't matter. It's all about the dimensions of the bottle. And then you have this sort of opposite end of that spectrum, such that like the interplay between bottle opacity and the dimensions or shape of the bottle combined are important to explain that response variable of that time until the beer goes bad. And then I go on a little bit of soapbox about highly collinear variables. And so it's a thing, especially in sort of when we have climate data, to just throw in a lot of covariates to say, here's temperature in January, here's temperature in February, here's temperature in every month of the year, as if those are going to be informative covariates when inherently they're like kind of not, right? It's something about the composite function of that. It's something like seasonality. It's something like min temperature in a year, max temperature in a year. It's rarely a process where you can make inference and say, you know what's important is the temperature in February. It's not true all the time. So things like phenology are a good example of when like maybe you want to actually incorporate the inherent nature of the time series. But for the most part, models just mashing in a bunch of collinear predictors are not great. And what I mean by collinear predictors is that there's an inherent relationship between temperature at time t and temperature at time t plus 1. So the mean temperature in January in Louisiana is going to be related to the temperature in February in Louisiana. More so than the temperature in February in Antarctica. You have to like sort of fundamentally accept that there is a temporal collinearity. There's a temporal correlation in the structure of climate and many variables that we'll encounter in ecology. Some ways around this are dimensionality reduction, which is a sort of aspect of feature creation. And so taking all that variation and trying to smash it into as few axes as possible, which are non-collinear and which are orthogonal. And so things like PCA or principal components analysis can sort of start to get at that. And there's many, many other sort of feature reduction techniques that you could use, which I don't do here. All right, now, yeah, I actually switched gears a little bit. And so now this talks about sort of collinear variables. Oh, sorry, getting a little water. This doesn't talk about collinear variables, I'm sorry. This talks about categorical variables and the idea of so not all of our variables are inherently continuous. We don't have a continuous x1 and a continuous x2, but we have something that splits along categorical or factor vibes. So things like biological sex could be used. So if you're going to just define it in a sort of binary sense, which is not a great idea, but let's say you have male and female of some species, and you want to say, is there a difference between these two in their relationship between Y and X? That could be really important. And so I give a sort of ham-fisted example here where I set up, I'm just going to run through it and then look at the sort of head of it. And I stored this as dat2, where we have our Y variable, which is still drawn from a uniform distribution, bounded between 0 and 1. Probably not ideal. I should have just gone R norm instead. But for the purposes of this, it's fine. And then we have our continuous variable x1, x.1, and our categorical variable x.2. And so our categorical variable can only take two values. It's either A or B. You're either A or you're B. And we can now load this into the LM as an additive term right there. And now, oh, we're going to plot out the data. Oh, wow, those are way messier than I thought they were going to be. I thought I built in some inherent like structure to them. This is just a big mess. And so we can look at the summary of the actual model as trying to explain it. And like that's not really surprising, where our x1 variable, our continuous variable, wasn't able to explain much variation in our y variable. And so this is sort of demonstrated by this very sort of everywhere appearance of the relationship between x and y, or that x1 and y. Also, we had no effect of our categorical variable a and b. And so categorical variables in R are structured always comparing some first level to the other levels. And so here we won't see a slope or an estimate for A and B, it's only for B, because it's B in relation to A, meaning that the slope coefficient would be interpreted as the amount of increase in Y that you would see for dependent on A. Yeah, that makes sense. A little bit less sense than it should, but the idea here, by incorporating information on categorical variables, we can sort of fundamentally get at different slopes of the relationship between y and x, our response variable and our continuous predictor x1. And so what I've done here is we have our summary of M8, nothing is significant. It sort of will make a little more sense in a second, but maybe it'll make sense now. And so what if we subset the data to just be only those where A is, right? And so we have some subpopulation A in terms of x2 that we care about, and we can build a model only considering those data. And then we can do the same, but for B. And so here I'm just doing a simple linear model as I did before of y1 as a function of x1, but I subset the data based on if it qualifies as A or B according to that x.2 covariate. And I can add in, let's add in the line of the, so we can use AB line, which that's a bad idea, because that only uses the first two. Yeah, that only uses the first two regression coefficients. So that's just going to get overwritten. And that's also not that informative. And so, but what I'm trying to show here is that the slope of the lines is the same, but the intercept is shifted between the groups A and B. And that's not necessarily true. The intercept can shift, or sorry, the slope can shift too. Let's see if we can rerun that, because now it's just going to generate random. Yeah, so the slope changes in some of these here. And so maybe they're in that blue line, it's not significant, likely. I don't think it is. But the idea is to start thinking about how this variable x2, when subset, could actually influence the relationship between your predictor y and your response y and your predictor x. And this is made clear by a concept called Simpson's paradox, where categorical variables or dividing up by groups can actually have a really strong effect. And so here I've just borrowed a really, really simple example. I think I found it on like Wikimedia Commons. I linked to sort of the code that I've modified somewhat, but not much. So props to the original poster of that from like 10 years ago. The person probably doesn't remember doing it, but thank you for making your sort of code and figure available. And so this idea, I'm setting up basically the variables here in a really arbitrary way. The idea that I tried to sort of exhibit in a very ham-fisted way with these blue and black points is that group delineation by some categorical or factor variable can really influence what inference you can gain from a model. And so Simpson's paradox basically says, you have a situation where you have these data, and let's say we didn't know that, we just ignored color and said these are all black points, we would fit a line. Let's assume that we can just like fit a linear model to 8 points that are distributed in such a fashion, and it would show a negative relationship, a likely non-significant negative relationship, but it would show a negative relationship. However, when you actually incorporate the influence of this other variable x.2 that's categorical, you see that there's actually a positive relationship between y and x. And here I'll add the lines from the linear models in, where the dashed black line corresponds to the overall fit linear model, which is a crap model, right? It's not good. And then, I mean, given 8 data points, and then given our lines based on 4 data points, between just the black points, which provides a really good fit, like a really tight fit, as well as the blue line, which provides a good fit to those data, but both those slopes are positive. Meanwhile, the overall relationship is negative. It's called Simpson's paradox. It should be in the back of your mind. It's more of a cautionary tale about what predictors are important to your model and to your given response. And so the model is only as good as what you put in. This is not an advertisement to like throw everything into a model and see what comes out. I'm really against the idea of sort of dredging, quote unquote, and just finding like the best model, sort of irrespective of biological inference or meaning. It's not an ideal scenario. But also this is something we need to sort of think about. All right, so now we can actually think about what it means for a model to fit nicely and what it means for a model to fit poorly. And so we have our M6 model from way back in the day. And we can look at the summary of it. And we can start thinking about what makes it a good model, what makes it a bad model. So here was our y as a function of our x1 plus our x2. It was just the additive term. We considered both in the model. X1 came out significant, x2 is not significant based on this alpha threshold of 0.05. We can look at our adjusted R squared and we see, oh nice, we're able to actually explain around like 83% of the variance in our response variable given our x1 and x2 and our model assumptions. But let's test our model assumptions. And so R offers some nice ways to do that. Basically just calling a plot on a model object will create a series of 4 plots. And we can look at them now. All right, and so in the top corner, we have our 4 plots. I set the layout function so they're all just displayed at once because it's kind of nice. And so, excuse me, we have first our residuals versus our fitted plot. Ideally, this line should sort of hover around that 0 line. There shouldn't be any big outliers. But here there's like a clear general trend. And you know what that trend's caused by? Is caused by us defining our y in terms of being bounded between 0 and 1. And our, like, you see that sort of curvilinear relationship between y and x1. That's going to cause some issues in terms of these plots, which are like a sort of summary plots or our diagnostic plots. That's it. That's what I was looking for earlier, and I couldn't remember it, called like logistic. Our second plot is here, the normal QQ plot. Basically, you want things to fall around this line, this dotted line here. When they start diverging, it's a sign. It's like, that's not ideal, meaning your response variable is non-normally distributed, or there's something going on there. The other plots, I have actually less experience in sort of diagnosing them, but we talk about. The top right one is the scale versus scale location plot, where we have standardized residuals in the y and our fitted values in the x, which I guess we're just looking for no clear relationship. Because if there was a clear relationship, that would not be ideal. So things actually look decent there. And then in the final plot, the residuals versus leverage, I think we want things also to sort of be randomly distributed, but mostly like around 0. And so this pocket here is a little bit concerning, and I think indicative of some of the effects that we've seen in the other diagnostic plots, which relate to our data sort of being inherently bounded. So there's Y, there's X, and so X is a little bit skewed. Y actually isn't too bad, but it also is inherently bounded between 0 and 1. And so that does matter when we fit a linear model, which assumes normality, which assumes that our data are drawn from the same probability distribution that is bounded between negative infinity and infinity. And so here, like when I have data bounded between 0 and 1, maybe I'd want to use something more like a beta regression or something like that. Something that acknowledges that my response data are bounded between 0 and 1. By using a probability distribution that is bounded between 0 and 1. Makes sense. All right. And so now I'll like slightly diverge. And so we've talked about linear models, their complexities, a little bit like diagnostics and how to sort of suss out if you're violating the assumptions of the linear model, which like you can do a lot by just simply exploring the data. So you have a data set, it's going to be a little bit messy, but using something like a Shapiro-Wilks test, which tests for normality, or just like sort of plotting out your data and your X and Y to see what's the shape of the relationship. What do I expect to be the shape of the relationship between my response and my predictors? But now I shift a little bit to focus on predictive models instead of on models that are inherently used for inference. So I set up that dichotomy sort of early on, and the Bryman paper touches on this, where up until now, we've been focused on the influence of X on Y. But what if we really don't care at getting at the shape of that relationship? We really just want to know what Y is, right? So things like the number of like koalas left in the environment or something like that. Maybe we don't care if it's temperature or if it's precipitation or if it's hunting pressure or if it's this or that. Maybe we just want to predict the number. Like we just want to predict the overall number. We care more about prediction than we do about inference in that case. I think conservation biologists might hate me for that analogy, but we care about prediction, sort of inherently there. And so I introduced the idea there of maybe we just should fit that crazy spline, that like 15 order polynomial to minimize the variation given our data, though that won't be predictive. So we don't want to do that, but what if we don't care about inference and we just want to build a predictive model? And so here I'm ham-fistedly making new data, which I bound X1, which was previously, we can see in the histogram, bounded between 0 and 1. Here I'm going to hand the model data that are bounded between, oh no, just the first 10 values of X1. And then I'm going to hand it the first 10 values of X2. And so you can use the predict function. So predict is a function in R that you hand it a model object. And if you hand it no data, no new data, it'll give you predicted values given your data. So it'll give you the fitted values, the values that minimize the unexplained variance, that minimize the error in the best fit line. If you hand it new data, it will output only the values for those given new data points. And so the structure of new data has to be the exact same as the structure of the original data. I forgot what we called the original data, actually. I don't think it wasn't dat? It might have been dat. So that, and you see, they're mostly the same except for the Y. That's fine. I think that'll still work with the predict function, because it is sort of you're predicting Y. And here we say that we want the confidence interval back. And so the confidence interval gives the uncertainty of the model, excuse me, the uncertainty of the model in its prediction of that given data point. So the output is some value fit, which is supposed to be y, given the data that we handed to it, which were the x1s and the x2s. So let's form this as a data frame, and now we can plot out what this looks like. So this is a sort of callback of our y by x1, where x2 isn't featured. And we can plot our points that correspond to the actual linear fit, which this should look familiar, but now they're in red. Essentially, this is a line before that was essentially just a linear fit. It should only be 10 points though. What did I do wrong there? Oh, I didn't hand it new data. I should do that. I think what I was trying to, here, I'll plot the segments out. I think what I was trying to get here was the idea of variation along the predictor variable in the size of the uncertainty, right? And so you should expect more uncertainty where there's less data. And so we can plot out uncertainty using these confidence intervals where they're actually like fairly the same. So you can see here they're smaller for some odd reason where I actually wouldn't expect them to be smaller. I expect them to be smaller down here. There's more data, but the data are actually also distributed with a little more variance in that Y space. And then up here, they'll tend to be have higher confidence bounds. And you can imagine if you get beyond this region, right? And so if you're trying to predict beyond the bounds of the observed data, those confidence intervals are going to get huge really, really fast. So if we just plot, I'm sorry, if we just make the predictions be for that first 10 points, what it's going to show us are the prediction. That's not right. I did something wrong. Oh, I'm plotting it by entire x1, not by x1, 1 through 10, I think is the problem. But also those y values are like garbage. Oh, that's also not right. What is the problem here? It is, let's see, header preds. It's going to be something where it's like obvious after the fact, but so we have our preds, they're 10. Oh yeah, it actually is that. Our x1 needs to be the first 10 values, not the entire thing. So we can plot our black points. This is our actual data, and then we can plot our fit of those first 10 points, which correspond just sort of haphazardly to this region. And then we can plot the bounds, which it like recycles bounds. What's up with that? Oh, because our x1 is not bounded. This is what I get for changing the playbook halfway through. And so that's what that actually looks like. And so if you want to predict just a region of your data, this is a way to do it by handing it new data. New data can also be used, obviously, to predict outside the range of your predictor variables. In general, it's not a good idea because you're assuming some sort of linear relationship. You're assuming that this is just going to continue on to infinity. Like it's not going to like saturate or do some weird curvilinear stuff. It's just going to like continue on this trajectory. Pretty bad assumption, especially given that, remember, this is a linear model. It's this model. So it's not only going to assume like this curvilinear relationship that you see with your eye, it's going to assume this model fit relationship that is a line that you can just extrapolate out into no man's land. So when the temperature is 1000 degrees Celsius, a panda will occur with probability 0. Is a silly example. It's not a good idea. I'm going to move this over here so we can see our notes a little better. So lastly, I think we're I think we're running towards the end of the lecture. Lastly, we may want to sort of measure our predictive accuracy. So when we make predictions, we want to be able to say, like, are these predictions garbage? Are they good? And how we do that is we either gather new data so we have our data and we train a model on it, and then we go out and observe new data and we say, how does our model that we have that's built on these data do on these data? Does it do okay? Does it do really poorly? Who knows? Or we can accept the data for what they are, divide them up, chop them up, hopefully there's enough of them, hold some data away from the model, and then train the model on some subset of data. This is really, really useful, especially because it allows you to get at uncertainty in predictive accuracy or in predictions really well. And so here I wrote a function that samples the data using the sample function and holds out some proportion of the data. Here I'm holding out 20% of the data. So this function is called train mod. It has input of dat, which is some data that exists, and it exists with columns y, x1, and x2, as shown in these couple lines here on 416 and 417. But up here, I sample the data and I find the indexes that correspond to those those data that I want to like keep out of the model. And so I have my training data, that's what it's called. This is a train test split, and this is an 80-20 split, which is pretty standard across a lot of arbitrarily decided, not arbitrary, but. And so here I'm keep training on 80% of the data and then testing on my remaining 20% of the data. So I set up my train test splits. I then train the model on the training data here, and then I have an output that has the truth, which is the test data, and then I have the model predictions on the test data. And so I can run this and output my preds2 object where I train the model, and I can plot the predictions of the model versus the truth, which the model has never seen. And so this is what's called, or it's most likely in-sample prediction. That means that the predictions are being made in the variable ranges of your predictor variables x1 and x2 that are bounded between the data that you have observed. So this is not saying like, here's the range of x1 variable that you've seen. I want to predict this that has never been seen by the model. When you sample randomly like I have, what you're basically tend to be doing is saying, here's the range of x1, and I'm predicting within points in that range. I can go over more of that in sort of lecture and the intricacies of thinking about that. But we can train this model a bunch of times, right? And so each time we run this code, it's going to generate a different relationship between, and so you see that upper right plot is changing, and it's between the y-axis, which are the predicted variables, the predicted y variable, and the truth, which is along the x-axis. And you see, like the model's actually doing a pretty good job. They're generally positively related. But how positively related? Like, how do we actually estimate like model performance given this? Given model predictions and true performance for a regression problem, not a classification problem. So sometimes you're going to hit sometimes when your truth is a category in sort of multinomial classification, or it's binomial. And so in that logistic regression example previously, our predictions would be bounded between 0 and 1, but they could exist anywhere between those bounds. Meanwhile, our truth would only be 0 and 1. And so there's different model performance measures based on the structure of your predictions and the structure of your truth or your real data. And so here I go over model performance a little bit in a fairly high level. I'm borrowing a lot from some interaction and collaboration I've had with Anna Norberg and some colleagues in Helsinki. And so they outline a couple different ways you could view model performance. In terms of, they outlined 4: calibration, discrimination, precision, and accuracy. Of these 4, I think the ones that I'm most familiar with are discrimination and accuracy. And so calibration refers to statistical conditions between distributional prediction and true values. All right, so calibration are the distributions between your predictions and your truth about equal, or are your predictions really like this and your truth is actually like really narrowly distributed? That would be bad calibration. You want the sort of overlap to be solid distributionally. Discrimination is your ability of the model to rank variables, to rank your response variable based on your predictors. And so that's really only, I mean, I think a Spearman's rank correlation can be used on continuous data. Discrimination tends to be a more classification focused model performance measure. That means when you have a y variable that is binomial or multinomial, meaning it can take a 0, 1 or a 0, 1, 2, where those are categories, not like actual it doesn't mean 1 or 2, it means A, B, or C. Discrimination is more useful there, I think. But I mean, I can also imagine a situation where you could discriminate via continuous predictions and continuous observations. Precision is also called sharpness, measures the uncertainty in model predictions for a given prediction. I actually don't even think we touch on precision here. But it makes sense, like in that sort of classic like dartboard example, like accuracy is your ability to like hit the bullseye. No, accuracy is your ability to sort of minimize variation around. No, it's precision. I'm gonna edit this later, hopefully. Precision is your ability to like group darts wherever on the bullseye. Accuracy is your ability to hit the bullseye consistently. And so here I talk about one specific measure of accuracy, which is, and for 2 continuous variables, which is your sum of squared errors. And so basically what you do is you simply take the difference between your predicted variable, your predicted y, your predicted response, and the actual truth, the actual y or response, and then you square it to make sure that it's non-negative. So that's what I've done here. We can view accuracy here. And here we have a vector of length of our output. So we have 20 because we had 100 initial variables, 100 initial observations. And we held away 20% from the model. And so we have 20 variables there. And then we can take the square root mean of them. There's a bunch of different measures. This is root mean square error, where I take the mean deviation and take the square root of it. So I messed that up. And get some variable where if it's closer to 0, it's good. And if it's further away from 0, it's bad. And that's useful. That is a useful measure of model performance. But it's a very, very simple example of how we can actually measure model performance. And you can imagine that this square root mean of accuracy is actually going to change depending on the data. So if we run this again, so look, it's 0.1412 something. We rerun this code to train the model again on a different random set of holdout data. We then look at accuracy and we quantify accuracy again. And now we have 0.117. And so understanding the uncertainty in accuracy is really, really important. And so I'd suggest sort of getting into that mindset. If you're going to build a predictive model, build a predictive model that can be run a bunch of times and that you can get uncertainty of your predictions. Otherwise, you could run into a situation where a point estimate really doesn't tell you that much. So a point estimate of accuracy could belie a huge uncertainty in your accuracy. All right, and then lastly, and this is like relatively off topic, I go into tree-based methods here, and I call it like under the title of machine learning. But we talked about this before. We talked about tree-based methods, and one of those methods was gradient boosted machines or boosted regression trees. I have a whole big text block of me doing a bunch of hand waving and telling you to read different texts. If you wanted to get more into the ideas around machine learning and ideas around building good models, I would recommend The Elements of Statistical Learning by Hasty and others. Do I link to the book? I don't know if I do. If you wanted to get more into Bayesian modeling and understanding that, which I have not touched on at all, Andrew Gelman's book, as well as like BDA3, that's the classic. Ask me about it. I can also, if I remember, I'll link to it in the description. It's fantastic. Basically, the idea of tree-based approaches, and specifically sort of boosted regression trees, is to build a bunch of weak learners where you have imagine like if you just built like a linear model based on, with a binary split, you said like, here's my response, and I'm gonna bin my response into two categories based on my X variable, which is continuous. I'm gonna say anything less than X equals 0.2 goes into this bin, and anything more goes into this bin. That's probably a really bad model, right? But if you iteratively do it and say like, oh wait, okay, so I take the residual variance from that really, really simple model that I just made, and then I make a new tree and I say like, oh, but what about the influence of some other variable like x2? And so that has one layer, right? And so you can imagine a situation where it has two layers. And so here you say any response variable y, sorry, any predictor variable x less than 0.2 will lump into this category. Anything greater will lump into this category of the response variable y. And then I can have another layer. And so the other layer would be x2. If x2 is equal to a, then it's this value. If x2 is equal to b, then it's this value. But you still have this other branch of the tree. This is why it's tree-based methods, binary splits. And you can say, oh, this is a different relationship than this one. If if x2 is equal to this, is equal to a, then it goes to this, and then if x2 is equal to b, and then it goes to this. I think that makes sense. Hopefully it makes sense. Basically, the tree-based structure allows for nonlinear interactions between variables. Pretty useful. I think I mainly bring this up to introduce you to other concepts, and it might actually just be, hopefully not just to like flex on that linear model. So before we had a root square mean error. So we have a GLM accuracy, 0.135. And then, so what we've done here is train the GLM and also train the gradient boosted machine, which is this machine learning approach that allows for variable interactions sort of more loosely. And now I assess the accuracy of both methods of GLM and GBM using root mean squared error as our measure of accuracy. And now it's like the moment of truth is like, do the GBM, does it perform better? Just barely, just freaking, it's a really simple example, right? Remember, but it does perform better. And so we can say like, oh, nice. So modeling choice matters, right? Like let's see if it maintains it. And so now we've run it on a different subset of data. And now I set the seed. Wasn't that what it was before? No, it wasn't. So now we have 0.117 for GLM accuracy, and we can look at GBM accuracy. It's like ever so slightly better. That's probably consistent. GBMs are solid. But it is important to note, as I've mentioned earlier, that the random subset matters and understanding that uncertainty matters. What doesn't matter is when you try to get at differences between models by iteratively training models. Here's what I mean. Here I say I have GLM accuracy is 0.108 and I have GLM accuracy is 0.1175. I have my GBM accuracy at 0.108. Are those different from each other? Like, is there an improvement? You may be tempted to train a bunch of models on different subsets of data and then compare the distributions and say, here's the distribution of GLM accuracy. I guess this is a histogram now. And this is the distribution of GBM accuracy. And now we're trying to compare these two distributions. I would caution you very, very strongly against that. And I go into why in the lecture notes, but here it would take too long to run. But basically, the statistical significance of the distributional fit depends on the mean and the standard deviation of the distribution. However, if you ramp up the number of times that you randomly subset those data, train a model, and then predict, you're going to shrink those confidence intervals, right? And so here, this is the GLM accuracy distribution. It's bounded between here and here, and just imagine it's normal. I'm sorry, I can't draw on a chalkboard right now. It's just really frustrating me as well. It sucks. I'm a huge whiteboard drawer. I walk back and forth. I can't do that here. So this is GLM, this is GBM. And so here they overlap and they may be huge. This is not a real difference, right? When I do maybe 10 or 15 iterations of the pulling random, and so getting at that distribution of accuracy, as you increase the number of times that you retrain the models and reassess accuracy, you're just going to shrink those until you see a difference that doesn't really mean anything. So I would caution you strongly against that. I can recommend you papers that go over sort of how silly it is to use significance tests on these sort of model results. And here, yeah, I go over sort of like a t-test when I train it. So here I trained it on 10 models, which we can do in a fairly reasonable amount of time. And so it's going to go through and blah, 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 blah for 10 times. But then I do it for 2,000 times. And at first I set that to 10,000 and it took an hour to finish. And I was like, this is not reasonable. But feel free to play around with the code and just to show this, to demonstrate this for your own sort of edification. This is a thing. So here we can now compare the distributions using a t-test, which doesn't compare distributions. This just compares means of distributions. So we have our GLM-A, which is of length 10, and we can look at the mean of it. It is 0.134, and then we can look at our GBM-A. It is of length 10. It has mean of 0.1200, blah, blah, blah. We can perform a t-test on these two vectors and come up with not a real difference. It's arguably different. I don't know. It's really small. But as you increase sample size, it's going to get big, and it's not any more meaningful. So yeah, hopefully I haven't rambled on for too long. This has been a good introduction to modeling, hopefully. I covered largely generalized linear modeling in a really superficial sense. I think a lot of this will go over more in class when we talk about the constraints of models, the assumptions of models, and what models can sort of bring to the table in terms of inference versus prediction. And with that, I think this is my last lecture. So thank you all for joining. If you're not at LSU, that you're awesome. Thanks for sticking around. Feel free to comment, like, and subscribe. I don't know. Don't do that, but take care and thank you.